How is multiple regression related to other statistical techniques? This final chapter runs through a long list of statistical procedures and statistical techniques that are connected more or less to multiple regression. I do not have time to cover any of these in real depth, but I have tried to provide a few references for additional information if you think that these models or these methods might be useful to you in your thesis research. How is regression related to t-tests for difference of means? Well, the t-statistic for the coefficient using the dummy variable is the same as that of a conventional t-test, and we see that there are t-test components to our regression analysis, particularly when we are using dummy variables. The advantage of doing regression is that you can control for other variables by putting them in the equation as well. So t-test is maybe okay for bivariate, maybe okay for dummy variables, but it's limited. So regression helps us to control for other variables as well. What about analysis of variance? Well, we talked about ANOVA earlier in the semester. Ellison's book doesn't cover ANOVA, which is why he's explaining a little bit about what it is. It's a method used to test whether the means of outcome variables are different across two or more groups. It's the same as multiple regression with a single independent dummy variable. For a t-test, we talk about only two groups. It's also equivalent to multiple regression when we have a single independent dummy variable. When there are more than two groups, ANOVA is equivalent to multiple regression for all but one of the groups. So some statistical programs actually use what's called a generalized linear model, and they don't actually talk about regression and ANOVA separately. So they don't talk about ANOVA separately or run ANOVA separately, except within that context of the general linear models. So really they are the same thing. ANOVA is a simplified version. If you look at the equations that were calculated in the process of ANOVA, you'll recognize some of the square differences between, some of the square differences within. These are terms that appear in the calculation of regression as well. So that the covariance is between, the variation for each one, standard deviation for each one is within. So you're already dealing with those same language, the same terminology, the same processes when you're talking about multiple regression. What is covariance? Well, ANCOVA, as it's called, the analysis of covariance, is an extension of ANOVA that allows for situations where some of the independent variables are categorical and some are measured quantitatively. So we're not going to talk about ANCOVA. There's also MANOVA, which is multiple analysis of variance, again, very much like multiple regression. There are lots of variations that you can look into if you think that they may be useful for you in your future research. What is factor analysis? Factor analysis is designed to take a bunch of variables and to reduce them to a smaller number of dimensions. So suppose, for example, that we have 4 measures for health. Maybe we have BMI, the amount of time that someone spends in minutes exercising each week, the number of fruits and vegetable servings that they eat each week, and the number of days in the last week that the person said that they were limited in activities due to poor health. So we have 4 dimensions, 4 different measures, 4 different variables for health. These are definitely going to be correlated with one another. And if we stick all 4 of them in the model, we're going to come out with multicollinearity issues, right? They're not perfectly collinear. Somebody can eat lots of fruits and vegetables and not do any exercise at all, but we would expect that people who are high on one of these measures are also going to be high on other of these measures. If we put them all in the model, we would end up with something that's very inefficient because of the multicollinearity. So when we have multiple indicators of a particular dimension, so we sort of organize them as a group, then we can use an index or a scale or talk about them together and measure what are called factor loadings. So factor loadings allow us to determine which of these multiple indicators using factor analysis is the most influential on the model and the most influential on the other elements of it. So we take together groupings of variables that are multiple indicators of a particular concept, and we talk about them as being connected. They're representing a dimension, and that dimension might be health. So we can talk about that. I have a link at the bottom to a really good kind of simple overview of what factor analysis does that may make it more clear. Path analysis is essentially a way of representing the set of regression equations in a causal diagram. So we can look at how the coefficients are connected to each other, how the variables are connected to each other. So in path analysis, the alpha and the beta coefficients are estimated separately for each equation by using OLS, and then the different elements are diagrammed together, put together in a visual model that indicates how these relationships are connected and what the regression coefficients are for these relationships. So simultaneous equation models are path models that flow in only one direction. Non-recursive models flow in multiple directions. We can see this element is it only flows in one direction, but occupational and educational aspirations obviously are connected to each other. And so we see this as a non-recursive model overall because we believe that all of these things sort of end up connecting to each other. Usually the numbers in the paths represent standardized regression coefficients, and that makes it easier for us to make comparisons among the variables in the path model, but allows us to visually identify the direction and impact of the relationship between two or more variables. Structural equation models are combined, what we call confirmatory factor analysis and simultaneous equation models. And the basic idea is that the larger model takes into account both observed variables, ones that you've gathered data on, and unobserved or latent variables that are impacting but not being directly taken into account in the model. So we can measure mother's occupation and mother's schooling, and what we're trying to get at perhaps is mother's socioeconomic status. So we can't observe that, but we are able to gather data on occupation and schooling and make an estimate of this unobserved or latent variable. And we believe that impacts sons' SES through their schooling and their occupation. So we are gathering data on the schooling and occupation of mothers and fathers and the impact that it has on their schooling, as almost you can think of it as a proxy for understanding how parents' socioeconomic status impacts a son's socioeconomic status. So these are often represented as path models where the observed variables are rectangles and the unobserved variables are ovals. And the best programs for doing structural equation modeling is Listral and AMOS. Those are the ones that do it most readily. I think that that's still true, that there haven't been some additional ones that have come out. I don't know how well R works with doing structural equation modeling. I can tell you that when I was in graduate school, structural equation modeling was the most fashionable and popular thing that you could do. So everyone was doing structural equation modeling in the mid-1990s when I was in graduate school. You don't see as much of it today. You see some other models being used more frequently. Multi-level models are also called hierarchical models, and they are designed for data where the observations are naturally clustered into groups. So you can think of an example of a sample of students within a set of classrooms. We talked about the problems of having data that was aggregated, and this is where this could come out. But also cluster data is vulnerable to multicollinearity, and these hierarchical models can address this in a way that ordinary least squares regression cannot, because it can take into account the fact that you would expect students in the class to have similar experiences and therefore answer in similar ways to particular variables. What is nonlinear regression? Nonlinear regression is widely used by economists to construct theories about economic relationships, And it's similar to ordinary least squares regression, but it involves repeated approximations to find a best fit. So it is based on an iterative model, an iterative algorithm. And they start with a reasonable guess of the unknown parameters and then go through an iterative process of repeatedly measuring by inputting those improved measures until they get one that doesn't improve from one generation of iteration to another. It's used pretty often to look at things that are believed to be nonlinear, like economic relationships, large-scale economic modeling.